Now, after having created the ions, the next step, and the fragments, the next step is to separate those fragments according to their mass to charge ratio. And there are several ways you can do that in equipment used to analyze biomolecules. A very popular analyzer is something called time of flight, and you will hear a lot about TOF mass spectrometer. They are very popular, and the ions are separated by different velocities as they move in a straight path towards the detector. And its time of flight allows very rapid, and it's a very popular technique because it is very quick, and it allows a very rapid analysis, and it has a good resolution and very good accuracy. Also, it can be used for any mass range, so that which is particularly popular because it allows you to identify even from very small molecules to very large ones. You can have different types of time of flight, different type of TOF analyzers, and you can have a linear pathway, and you can see the resolution is okay. You can have what is called a reflecting TOF, and as you can see in the spectrum below, the mass resolution is much better, and that clearly is reflected in the price of the instrument. Another popular technique for ion separation using mass spectrometry applied to the study of proteins is a quadrupole. This is a schematic diagram of how a quadrupole looks like. And it was first described in the mid-1950s, and it works by separating the ions according to the mass to charge ratios using a quadrupolar electrical field. So you've got 4 perfectly parallel rods. You have a constant DC voltage and a variable RF radio frequency voltage. The different ions will go through the quadrupole, and only if they are in resonance with the frequency they will go through, the others will be deflected. And by varying the RF voltage, you build up, you let the different ions go through, and you build up your mass spectrum. Another way of separating ions in mass spectrometry applied to proteins is the use of ion traps. It uses an oscillating electric field, and there are 2 types of traps. They can be 2D traps and 3D traps. The ions go through the trap, and they become trapped on a 3D trajectory or a 2D trajectory, and they are expelled from the trap according to their mass, and that's how you produce a mass spectrum. There are also new or more modern types of traps. For example, the Orbitrap, which is a relatively new type of mass analyzer, and it's just another way of trapping the ions to then being released and detected by your detector. It is also reflected in the price, but their accuracy and mass resolution is much higher compared with time of flight and quadrupole analyzers, and it uses an electrospray ion source and 3 sets of quadrupoles, and then this Orbitrap mass analyzer. And another type of special trap is called Fourier Transform Ion Cyclotron Resonance, FTICR. And it's just another way of trapping the ions and then releasing them to produce in an orderly fashion, so it can be detected and a mass spectrum can be produced. This is a schematic diagram of how an FT ion cyclotron resonance looks like. The different mass analyzers mean different degrees of accuracy and resolution, and this table compares the 4 most typical mass analyzers, and as you can see, from quadrupole to TOF to Orbitrap to FTICR, the accuracy improves enormously. The price of the instrument also increases considerably. So that's another consideration, that most instruments to perform mass spectrometry of proteins or biomolecules will be a MALDI-TOF, so MALDI ion source and a time of flight as analyzer, or an ESI-TOF, electrospray ionization as ion source, and TOF as the analyzer. There are other combinations that typically are linked to an ESI as an ion source. But MALDI-TOF and ESI-TOF are definitely the most common ones at the moment.